If the OSI model still feels like 7 disconnected layers, this lesson will make it practical for CCNA exams and for real troubleshooting on live networks. We'll connect the layers to protocols, devices, PDUs, and the kinds of clues that show up in exam questions and day-to-day support work. Early networks often worked in isolated ways, so equipment from different vendors didn't always communicate cleanly with each other. Standards gave everyone a shared language, so devices, protocols, and network designs could interoperate instead of depending on one company's rules. As networks grew, the industry moved towards shared protocol suites, and TCP/IP became the practical foundation of modern networking. Layered models matter because they separate jobs clearly, which makes design simpler and problems easier to isolate when something breaks. For CCNA, think of OSI as the reference model you use to organize concepts, while TCP/IP reflects the protocol stack used in real networks. They are related, not competing answers. The OSI model breaks networking into 7 layers, while TCP/IP groups those same jobs into 4 broader ones. At the application layer, user-facing network services live here, like web, email, and DNS requests that software relies on. Presentation handles translation, formatting, compression, and encryption, while session manages the setup and maintenance of communication between hosts. Transport is where TCP and UDP sit, so think segmentation, reliability, ports, and end-to-end delivery between applications. Network is the routing layer. This is where logical addressing with IP and path selection happen across networks. Data link handles framing, MAC addressing, and local delivery on the same network segment, which is why switches operate here. Physical is the actual signaling layer. Cables, connectors, radio waves, bits on the medium, and interface status all point you here. From top to bottom, remember application, presentation, session, transport, network, data link, and physical. Use a mnemonic if it helps, but make sure you also understand what each layer actually does. When an application sends data, the message starts at the top of the stack and moves downward through the layers. At transport, the data becomes a segment. At network, it gains IP information and becomes a packet. At data link, it becomes a frame with local delivery details. And at physical, that frame is transmitted as bits across the medium. On the receiving side, the process reverses. Bits arrive at the physical layer and move upward through the stack. Each layer reads the control information meant for it, removes what it added, and passes the remaining data higher. By the time the data reaches the application, the headers have been processed and the original message is ready for the software to use. TCP is built for dependable communication. It tracks data, expects acknowledgements, and can retransmit when something is lost. It also keeps data in order, which matters when applications need the exact stream reconstructed correctly at the destination. That's why TCP is used for traffic, where accuracy and completeness matter more than raw speed. A TCP session begins with the 3-way handshake. One side sends SYN, the other replies with SYN ACK, and the first side answers with ACK. That exchange confirms both sides are ready and establishes the connection before real application data starts flowing. Flow control then helps regulate how much data can be sent, so a fast sender doesn't overwhelm a slower receiver. One common trap is mixing up MAC and IP addressing. MAC is data link for local delivery, while IP is network for routing between networks. Another is confusing devices by layer. Switches mainly live at data link, and routers operate at the network layer. Also watch protocol mapping questions. TCP and UDP are transport, IP is network, and Ethernet sits at data link and physical. When you're troubleshooting, the OSI model gives you a method. Start low with physical checks like power, cabling, link lights, and interface state. If the link is up, move to data link and network. Check VLANs, MAC learning, IP addressing, subnet masks, and default gateways. Then work higher if needed. Ports, sessions, encryption, and application behavior can all narrow the fault to the right layer fast. You should now be able to recognize the OSI layers, map key protocols and devices to them, and follow data as it moves through the stack. Keep practicing with exam questions and troubleshooting scenarios, and this model will start to feel like a real tool instead of something to memorize.